Exploit blockchain.
So, what do we have there? Secure hardware analysis. Maybe I should start by mentioning my name because it's not on the slides. What can I do here? I can maybe write it. Michael Schloh von Bennewitz. So you all wanted an autograph, didn't you? Now you have one. There you go. Yeah. And before we get started, the live autograph, the only autograph live on stage on the day. If my speech gets too boring for any of you, there is a switch on your headset. If you push that, the speech stops. Okay? So let's get started. I'm going to start with a demonstration, if that's okay with you. We'll start the camera application. That's not the camera application. Camera, there it is. And and there we have a camera. You like that? So everything is ready, and I'm going to be using this bus pirate. This is called a bus pirate, and it's useful for serial analysis of hardware circuits. What I'm going to do is tap into an integrated circuit using this Pomona clip there. See how that opens and closes? And on the end, you can see some metal contacts. Doesn't focus very well. So what shall we hack? We're going to hack some PCBs, if you'd like. Here's something that we created in Prague just a few days ago. Not sure if any of you were there. Was anybody in Prague for the HCPP last week? One person, two persons, almost everybody in the room. Great. So we're going to do a couple things. You see, there are a couple. Can I have the laser pointer, please? So there are a couple. There's a couple chips on here that you can see. And it's not very good, but they're at the top there by the buttons. You see those? Now there is an intended way to access them, which I won't demonstrate. They are EEPROMs, and they use radio frequencies to read and write data over NFC. We're going to access them using these clips and a bus pirate. The first thing we want to know is what the address should be. So here's the data sheet for the chip that we're talking about. It looks just like this here on the left. And so let me get my... So that's what we're looking at the top of the camera. Do you see those two? This and that, U1 and U2. So here's the data sheet, and what we're going to look for is the address, the I2C address, and it looks like that is on here. I2C timeout period, so page 59. That will tell us what we're looking for. So I'll go right to page 59. There it is. So once more, we have we basically have the address 10101110 and then either 0 or 1. What this translates to, if we put this into a calculator, I'm not sure how to get some programmer calculator, binary. Let's do binary here, and we have 11010101010, and 1100. So what do we have there? We have AC. Do you all see that? So that should be the I2C address. Let's hack the chip to see if we can get that. So the first thing I will find the COM port, that is COM6. We'll use PuTTY. We're going to change COM1 to COM6. It's 115.200 is the baud rate. And there we have our bus pirate. Let me make this a bit bigger for you, and we will be able to see a lot more. This is just about that time when you push that switch to turn the boring off. Anyway, so here's the bus pirate. It's giving us a list of commands, instructions, functions, features, things that we can do with it. We're interested in I2C because that's the type of chip that it is. So I will give 4 for the I2C. And we'll just choose any old speed at all. And we'll look at our voltages. We'll turn on the voltage. There we have 3 volts on the proper chips. Turn on the pull-up, and we'll choose a 7-bit address search. And as soon as I clip the Pomona clip onto the device, we should be able to scan. Let's do that now. So I will clip this on there. You see how that got clipped on there? That's not supposed to happen. Okay, so we'll move on. That was supposed to give us address ranges. Just like here, it shows the address ranges. Maybe we'll return to that later. And back to our slides here. So basically, what we were taking a look at is the first of those. We were looking at the I2C. What we also have in hardware circuits is SPI, or serial peripheral interface. All of these things are attackable from a hardware and physical standpoint using clips like the Pomona clip and a number of other things. We'll take a look at the hardware tool sets, which I can visually represent here with the camera. We've already seen the bus pirate there. When we're when we're looking at chips this small, you can see the size according to my finger. Then it helps to have a structure where we can plug that in. So that's simply this opens and closes, as you can see, and on the bottom there are contacts. That's one hacking tool set. Here's another. This one is called a chip whisperer. This one is called a chip whisperer and is useful for side channel analysis. So this means attacks that involve voltage glitches, voltage spikes, timing attacks with clock glitches, and CPA or correlation power analysis, these type of attacks. Here is a very simple, passive Ethernet tap, LAN tap, which is very much becoming very popular. In fact, I brought this with me for one reason. I believe if you've seen the Bloomberg reports of recent, they were talking about tapping Ethernet lines and sending them out over the network, the internet, selectively. Oh, that's useful. Shall I switch? All right, that's a little bit better. Right, so this is much smaller than the chips that we were looking at. This one here. They're simply different formats. They're simply different package sizes, is what we call them. And the ones that they found in the supermicro computers were doing a similar thing that you can do with the LAN tap that I just showed. I believe there is, I have it here in the slides, in fact. So this is what happened in all of the, or not all, in a select subset of the supermicro servers that were shipped out of China and arrived in United States locations. It's a quote, so I'll just read it. Unusual communications from a supermicro server and a subsequent physical inspection revealed an implant built into the server's Ethernet connector. I mean, so we're not going to find things like this because it's simply very big. But as you saw on the tip of the finger, these can be shrinked and minimalized to become active circuits that fit just about anywhere. There is I thought I had it. There's a great website for this, but I won't be able to find it quickly. Anyway, so these are some of the chip footprints. We've already seen this one here, the SOIC, or the small outline integrated circuit. There's several others. Some are very small, like the WCSP, for example, is very, very thin, difficult to solder, and you don't have these legs sticking out. If you notice, there was all of these contacts that you can physically see on these chips, although they're very small. You can actually see those tiny legs. I think if I make this a bit bigger. And the other package sizes have less contacts directly on the chip. You can still clip onto them if you take the chip off. So I've brought a few devices up here just to drive the point home, to understand what type of devices are maybe worthwhile attacking, and for that same reason, the designers should be considering protecting with various hardware features. So that one there is a very simple device where we're storing data of all kinds in these two EEPROMs, in the U1 and U2. Could be telephone numbers, could be harmless text data or browser URIs. It just so happens that this badge belongs to a conference in Prague, and they were storing secret keys associated with cryptocurrency wallets on there. So this becomes already a very nice attack target. Let's see. So here's something else that's not directly related to blockchain or cryptocurrency, but it is a RF, a radio frequency device, which transmits LoRa frames, or long-range radio frames. Why it's relevant to security and hardware security is that we do have these crypto chips on the side, right? These are actually, I have some samples here. If we can get the bus pirate example demonstration working later, we can try tapping into those. And the reason that you want to choose cryptography in an RF product, in a radio frequency device like this, is to encrypt data before you send it out on the public airwaves, right? So that you have a point-to-point connection in between. You're using public airwaves, but your data is protected along the way. There are a couple other examples, but I'll just go right to the crown jewels, so to speak. So these are hardware wallets. You can probably see the Monero logo on the back. This is what I'm doing most of my time with either doing badges or hardware wallets. And in case you're wondering what one looks like while it's working, I'll demonstrate that too. So there's a hardware wallet. Turn it on. There's the Monero logo. There's some buttons at the bottom. As you can see, it's got a USB-C connector. Make a new wallet. Oops, I gave you the mnemonic secret key. No, I'm just joking. So when I turn the power off on this, it vanishes forever. There's nothing written on there. Right, so it gives me the option to go back and forth. This is kind of a prototype device. And it has, instead of 24, 25 words in the mnemonic, because that's what Monero uses. Has a few other a few other differences. There's the address, and here's a QR code, right? And so that's kind of how a wallet works, a hardware wallet, in case you didn't know. And if we were able to tap into this and steal the secrets, then we would have control over all the funds in the wallet as well. So that makes this worthwhile attacking as well as designing properly. Right, I have several other examples, but we're not going to have time to get to those. One of the things that some people don't understand about these low-powered, microcontroller-based platforms, hardware platforms, is that the storage is on the chip itself. So when we have things like this wallet here, then that big chip in the middle, that is inclusive of all the firmware. So the source code that's running on this is not on a hard drive, a SSD, or any place like that, or a SD card. In most cases, it's directly on the chip itself, which means we have to program it specially. This is an ARM Cortex M4 microcontroller, or it's an M4, I believe. So there are some programming tool sets. I've radically reduced the selection here. We have probably over a dozen, like Arduino is one, the Arduino IDE, and then we have things like proprietary ones like Kyle or IAR Workbench, all kinds of stuff. I prefer this one because it's open source, and it's called Platform IDE. Just wanted to show that quickly. Once you develop firmware for a platform, a hardware device, you have to flash it using a special serial connection like we saw before, one of those earlier slides. It's called JTAG. There's some others like single wire debugger, SWD. So I never like talking about problems like tapping into chips, reading out data, side channel analysis, and data theft, these kind of things, without giving a few examples of protection, how to defend your hardware while designing it against these type of attacks. So a few things that we can use in our tool set of hardware design. There's the concept of fuse locking. Each of these microcontrollers is very common for microcontroller design. They have fuses inside. And fuses, if you don't know what that is, kind of a control of whether voltage passes or not. When the microcontroller is functioning, it reads the different fuses as it begins, as it boots. And depending on how they're set, it might operate at a higher clock rate, for example, a higher frequency. It might allow access to some of its interfaces to JTAG, or it might allow a bootloader to be overwritten. And what we want to do is lock that down. If we've already created a bootloader that we're satisfied with, if we have everything in place, if there's keys and signatures, then one of the methods of reducing risk in thieves taking the data off of there with ingenious methods like adding their own firmware, rogue firmware on the device, is locking the firmware down. So, for example, these two functions, this is actually two different, these are two different programs. Oops, I can't, it seems the battery's out there. So the first one, the thing that we're looking at is here, it's called Memory Protect. And this one is actually an Atmel construct, which locks the bootloader. And after this, the bootloader can never be altered again, theoretically. That's helpful because if your bootloader is the thing checking for the application that's running in firmware, then it might have tricks up its sleeve, like validating a signature, something like that. You want to keep that in your bootloader. That's one method of reducing risk. Another one is, these are all kind of partial solutions, right? Like, most people don't like potting compound. It is sometimes used to make it more difficult for an attacker to use one of these Pomona clips, those blue clips that I showed on the camera. That would make it much more difficult for me to access the legs on all of these ICs, on the integrated circuits, the metallic parts. I wouldn't be able to put a needle on them to measure voltage. I couldn't use an oscilloscope or a logical analyzer as easily. Once that potting compound is poured into the circuit, it hardens. It's usually made of epoxy resin. And it serves as a dust barrier, so it blocks your circuits from moisture and from dirt, from things that could cause them to malfunction. But it also makes a physical attacker with oscilloscopes, with probes, with bus pirate, Pomona clips, and so on, kind of makes them work harder. And combined with other strategies, this is a good example of this is border crossings. If you can force the people at the border crossing to spend just an extra 10 or 20 minutes disassembling your hardware and trying to access it, making clones, then it usually makes a difference of whether you know that it's been intruded upon or not. So you can kind of combine strategies. That's certainly one of them. I wish I had a hardware with epoxy potting compound on there. I don't use it very much. Another thing we can do is use secure elements. Basically, what a secure element does is store some kind of secret or validate some kind of secret and provide things like fuses or special meshes. So when you try to drill into the chip using nitric acid or fuming acid of some kind, or ion particles in order to read the voltages crossing the lines, these meshes will interfere in some way. And once again, this is only really increasing the amount of time that attacks require to succeed. But this can be used in combination with other strategies. In fact, I can show that we do have here some Atmel secure elements. It's a bit difficult to show because they are very small. And in this situation here, I'll just use the mouse because the pointer is not very good. I can use my finger as well. If you look there at U3, U4, U5, those are a selection of secure elements that are actually not soldered on. I haven't populated them. But they look like this. I'll put this just right next to them. Can you even see that? Yeah, I think you can see that. Just the light a bit. See that chip there? So that's actually an Atmel secure element. They claim that it has a cryptic label on the top, which is not documented anywhere in order to confuse the attacker, or they don't know what type of chip it is. I may still try if I have time, but I was going to try to demonstrate that we can clip on there with a Pomona clip and using the bus pirate, read out the address of this chip, compare it with online documents, and find out what it is. So we'll try once more. That's all for secure elements. There are a number of manufacturers that make secure elements. I've listed a few here. The first two are my preferences because they don't require NDA signing, non-disclosure agreements in order to purchase the chips or receive samples, receive support, receive documentation. There's always a varying amount of obligation that when you sign a pact with these companies with a non-disclosure agreement. And the ones in yellow there, the first two, at least some of the secure elements that they sell and provide, they don't require a non-disclosure agreement with that, which means if you ever make a product with this, you start a project, you write source code, you're fully free to open source that source code in case it helps you increase your security anymore. A lot of these groups that are doing work, for example, our good friend Limpkin, who's making the Multipass Mini, or many of the cryptocurrency hardware wallets, their team member size is relatively small. These are just a few people working actively or with the knowledge of circuit design and what's happening at a low hardware level. So it's all the better to, or it's one of the reasons to open source the hardware designs and get more eyes on them. And it's kind of it's an argument that doesn't always win. You know, get more eyes on source code is nice sometimes, but it does make a bit more sense when your team size is small. And that's what you get when you can choose a secure element without NDA encumberment or non-disclosure agreements. Right, so that was the final portion of the speaking, and if I have time, I'll do one more demonstration. We'll try once more. Can somebody tell me if I have time? I'll assume I do, since nobody's taking me off the stage. So let's take one more look. We'll cross our fingers extra hard this time. And I think what I'll do this time, we'll do once more with the, we'll take this once more. And where is the Pomona clip is here. So I'm going to use the bus pirate. Clip onto here. That. We'll go back to here and look at our voltages, which is just fine. Not good. Could be forgetting something here. No, we'll try one more thing. We will try clipping onto this secure element, find out what it is. So I'm going to try it like that. You can see it's a bit crooked. We've probably got a 50-50 chance The pins are in contact, I believe. I hope. Oh, let's check it out. So once more. Do you think it'll work? No, we're not having any luck with the bus pirate today. And all of the other tests and analysis methods, like the chip whisperer, are very involved. They take a good 20 minutes to go through the procedures, build new firmware, and so on. And so, with that, I'll show the commands again, things that we can do with the bus pirate. Sounds like I'm a salesperson for bus pirate, doesn't it? But no, anyway, these are all of the serial protocols that it can handle. And I think with that, I will maybe pass around a couple hardware wallets for simple inspection while there are questions. So this is what they look like. And a couple of people have asked me to see them, so I assume there's probably a few in the audience. By the way, I'm passing out the ones that don't work. I've learned the hard way. I've learned the hard way, the really hardware way, that if I pass out hardware wallets that are in perfect working order, they don't always come back. So, yeah, so he's just distributing them for inspection. Take a look if you like and pass it on to your neighbor. And if anybody has questions about any of this, I'll take questions. Quiet audience today. So let's try this again.
Hey, I have a small question for you. So for these hardware wallets and security, so it seems like what you're talking about here is just physical hacks onto the wallet. So do you anticipate it quite easy for any hacker to intercept these hardware wallets to get them hacked? Or do you think it's like, what are you trying to prevent from the hackers here?
So, good question. Now, hardware wallets come in all types of shapes and sizes. Some are using secure elements, some aren't. It's unclear if that's a benefit or a distraction. I personally, my opinion is that secure elements do add value if you're using them right, if they're non-NDA encumbered. But to answer the question most directly, what the actual danger is, the risk, what is the attack surface of a hardware wallet? If I get enough information out of that hardware wallet and I'm able to deduce or actually extract a secret key, then place it back in the user's hands. For example, in a border crossing. In a border crossing, you lose your possessions for 20 seconds or even 20 minutes. That user, that owner, will not understand that you have control over their finances. You can track them because you have their identity, unless you're using Monero. But in most cryptocurrencies, there is not so much anonymity, and there's just a number of scenarios where you as a user lose. I'm not sure if I answered the question, though. If I didn't, maybe you can rephrase it. Yeah, okay. And before you ask your question, I just did another scan of the interface, and I just want to quickly say that this was a secure element. So according to Atmel, we're unable to know what it is because there's no writing on the top of the chip. What we've discovered is that it has an address of 60, and all we need to do then, go to the internet. I'm not sure if I'm connected. I hope so. No, I'm not. And we'll find out what kind of chip we have. To be honest, I can't remember myself, but I think it's an Atmel ATECC. Okay, so let's try. No, no, no. All right, I'll try this. Atmel 8 I squared C address 060. Was it 60? Yes. And we'll even give the number C0 as well. Let's see if we get something. There we go. So let's try reading this then. We just searched for the addresses that we discovered, and voila, we know the integrated circuit in question, and that's a secure element. So all of these protection methods, they don't always work. This is not a very strong protection method to simply not write anything on the chip, but you need to combine them, mix and match. Yeah, answer.
Actually, you have answered for the first my question about the Atmel product, and the second question for the maybe reverse engineering or maybe acquisition of additional information from this device, it's possible to use side channel attacks that can be maybe combined with another information, and in this way it's possible to hack this little chip. So how we can trust for this hardware-based wallet and why it's more secure than maybe desktop-based or web-based. So
I understand the question, which is there are side channel attacks, correlation, power analysis, things like that, which can be conducted on microcontrollers, which are integrated into hardware wallets. How to reduce the risk of a side channel attack succeeding. I think there's two developments recently. One is from the hardware manufacturers. They are implementing things like glitch factor suppression. What that means is when you send a voltage glitch onto the input lines or the core voltage, the VCC line of a microcontroller, the past generations would drop an instruction or skip an instruction or do something like that, kind of resembling a buffer overflow in the more monokernel, high-powered world. But in the low-powered world, what you end up with is you skip a block of code, which may be examining a password. That's what happened in the past. Right now, what we're seeing is that the new generations of hardware microcontrollers from all kinds of manufacturers, they have some kind of protection against these spike attacks. Okay. So they will absorb voltage spikes. That's just in a nutshell. There's several other risk mitigation factors that they're building into the hardware. Okay. And on the second front are the firmware developers, the ones who are writing the firmware that runs on the microcontroller. And just like improving random number generation by using better seed and methods like taking sampling from temperatures and so on, they can introduce noise.
Yeah, or maybe true random number generator.
Right. They're doing it twice, or they're generating the random numbers a random number of times. Another thing that they do is generate instructions while they don't need them. For example, you always want to minimize the amount of instructions you're running because you get to the next function faster that way. That's actually, these shortcuts are what are making some of the attacks so successful. If you don't do these shortcuts and you always do the same amount of instructions regardless of if you hit a fork in the path of the code or not, it can be used to defeat some of the correlation power analysis attacks.
Okay.
So it's firmware from the developer or hardware from the manufacturer is the way I see it.
Okay, thank you.
Sure. I think there is one more question, and then that's all.
Okay, one little question. So, is it possible to develop a more or less protected wallet storage for the cryptocurrency? Or, to your mind, is it possible theoretically, or applying these technologies you mentioned? So it's again the question of how hard, how much time is put into the investigating of the hardware itself to crack it in the long run. So can we put it that it is still possible to develop a secure device, or it is it makes it more secure, but not ultimately? Thank you.
Yeah, so I'll rephrase the question. I think you're asking if these hardware wallet devices add a lot of value to your secure handling of keys, or if it's maybe only an impression. And I would think that this depends on the use case. Some users are very advanced and others aren't. What hardware wallets try to do is abstract the difficulty of using a cryptocurrency from the user while increasing the security. They don't always work like that. And in fact, I think there's a panel discussion today which handles this topic very well, so maybe we will defer to them. But there are other options, for example, to put the hardware wallets away and use simple smartphones and try to keep them air-gapped, which in my opinion is a bit difficult. You've got a running monolithic kernel with a lot of modules. You never know what your closed source baseband is doing. You put it in airplane mode, maybe it's still radiating. So that's one of the ways to secure your cryptocurrency and your blockchain applications is by using specialized hardware, whether it's a hardware wallet or an air-gapped smartphone. You probably need a Euro shield, if you know what that is. It's a Faraday cage. But there are several ways to reach that amount of protection. I think that if a hardware wallet stays simple and is useful for the user, you might have a couple features like detethering, which allows you to detach it from a computer, but that it's added value for all of the coins. So that was a lot of fun, and I think we have our next speaker.
HackIT. Exploit blockchain.